So let me remind you what we did last time. So last time we have discussed some generalities of this program of starting from some six-dimensional theory, going through 5 dimensions, and then generating a class of theories in 4 dimensions. So today we will discuss a very particular example of this program, which is maybe the simplest one. So we start from a 6D theory, which is called the E-string, which we mentioned last time, and we discuss its compactifications on a torus. Okay? So we'll only consider today compactifications of E-string on a torus, and we'll produce a very large class of theories, nevertheless, because we have a freedom of turning on various fluxes. Okay? And we will see a lot of examples of symmetry enhancement and how this nice geometrical construction explains those enhancements of symmetry, emergence of symmetries in the IR, on a lot of very simple examples. Okay, so let me start by, in the first 15 minutes, I will go through these steps that we outlined by going from, by discussing something about 6D, 5D and so on, and getting to 4D. And in the rest of the talk, I will discuss the properties of the 4D theories that we obtain in this way. So first of all, we go to 6D. And in 6D, we have this theory, which is called the E-string. And as we discussed, this is probably one of the simplest interacting six-dimensional 1, 0 theories. This is the theory which is obtained by taking a D4 singularity and putting on it one M5 brane. So a single M5 brane on a D4 singularity. What is important for us is that let me call it GUV6D, the flavor symmetry of this theory is E8. Okay. And as we discussed last time, if you take a generic singularity with one M5 brane, say Dn plus 3 singularity, the symmetry will be D2n plus 6, which for D4, which for n equals 1, which is D4 in this notation, will be D8, and it enhances to E8 in this particular case. Another thing which will be important for us is that some people, namely Tachikawa, Omori, Shimizu, and Yonekura, in a series of papers, I think Yonekura, the most complete one in 2014, computed the anomaly polynomial of this theory and of many other theories, okay? Which is an 8-form polynomial. They used various techniques. One of the techniques they used is going on the tensor branches of different 6D theories and doing tricks with anomaly matching, like matching anomaly coefficients. So some of these techniques are rather straightforward, some of them are sophisticated. And they came up with anomaly polynomials for general 6-dimensional theories, and in particular they have computed this anomaly polynomial for E-string. So I will not write the full anomaly polynomial, it's some monstrosity, but I will just write a couple of terms to show you that it is some very concrete expression. So for example, we have such terms where this is the second Chern class for the R symmetry bundle. And then we have, for example, something which depends on the E8. And there are many other terms there are several lines of terms. But there are mixed terms, there are a lot, there are gravity terms, there are all of them. So this is the generic thing you should write, which is an 8-form, and then the point is, as usual, to compute these numbers, and they have fixed these numbers in various ways. Okay, so this is known due to this paper, and I encourage you to read this paper if you are interested.
Is the index of this theory known somehow?
The index, as far as I know, is not of the E-string in 6 dimensions.
Yes.
I don't think it is known. There were papers by Waffa and friends to compute something about some properties of the protected spectrum of this theory, but I don't think this is a complete there is a complete answer of what is index. So in this case, it is called E-string because there are some tensionless strings which appear in this theory, and they were analyzing these strings and trying to extract something about the spectrum of this theory.
But let me ask, there's this n equals 3 theory that you get by overfolding the n equals 4 theory.
Yes.
Could it be that something like that works for this? That you start with the M5 prime index and do some, because you're putting it, I don't know. Is that some sort of modding out, overfolding of the M5 prime index?
I didn't think about it, but it might be. But in general, I'm a bit skeptical of these techniques because even in 4D, they don't always work in a nice way. So when you have a gauge theory and you orbifold, sometimes you can come up with tricks which relate the spectrum, like of the daughter theory, to the spectrum of the theory you orbifold. But a lot of subtleties are involved. For example, there is another. What you can do is to take E-string is a little bit. This type of orbifold is not very intuitive. But say you can consider M5 branes on ZK orbifold, which is something very intuitive. So you can consider M5 branes on ZK orbifolds, and then you go to 4 dimensions. So if you don't have an orbifold, these are just these theories that Davide has discussed, these class S theories, and you can try to orbifold them. So in simple examples, this orbifolding procedure is rather straightforward, but say if you want to understand how theories corresponding to 3-puncture spheres work, I have no idea how to do this orbifolding procedure. So I don't have a good answer.
Yes, there would be a very strong check because we would have to get E8.
Oh yeah,
symmetry
yeah.
out of it.
That's right. Yes.
So you know if we were right.
Yes. Okay. So this is about the 6D. So important thing that we know what the anomaly polynomial is, and we know what the symmetry is. And
if you go for
yes.
singularities with M5 brane, what sort of level symmetry you get?
Okay. So as a side remark, so in general, if you put something on G-type singularity, the symmetry G-type singularity, so ADE. So you will get G times G symmetry. In the A-type, you get an additional U1, and then there are special cases. I have written down them yesterday, like when it is Z2 orbifold, and there are some reality properties that make actually the group enhance, and so on. So there is a story there. So here again, this is a D times, it's D4 times D4 for general number of M5 branes. For one M5 brane, it enhances to D8. And then for D4 singularity, it enhances to E8. Okay, so this is the 6D part of the story. Then there is the 5D part of the story that we also already mentioned yesterday. And the claim is that if you take this 6-dimensional theory on a circle and you turn on some holonomy which breaks E8 to SO14 times U1, okay, there is an effective description in 5 dimensions, which is in terms of SU2 gauge theory plus 8 hypermultiplets. Okay, and this will be important for us as we will use this 5D gauge theory description to understand what the compactification on Riemann surface with punctures is. And also to study, it will give us a nice description of flux in 5 dimensions, as we discussed towards the end of last lecture, in terms of domain walls, duality domain walls in this theory.
Sorry, if you don't mind, I'll go back. The partition function of this theory, you can presume.
Yes, you can compute, and you can. Okay, this is sophisticated. Okay, let me give some more details of this thing. So the claim is that this is a 5-dimensional theory. But it doesn't have a UV completion in 5 dimensions. It UV completes in 6 dimensions. So explicit symmetry that you see here is SO16 because it's SU2 gauge group, and then the symmetry is SO16. And then there is another symmetry, which is U1 instantonic symmetry, that you interpret it as a KK symmetry, as a Kaluza-Klein symmetry. So when you compute this partition function, Then there is, when you compute the partition functions of this theory, the claim is that you should reproduce the partition function of the six-dimensional theory. Okay, say if you compute an S5 partition function, in a sense you should get an index or some kind of an index of a six-dimensional theory. It's a complicated computation, and you can see how E8 appears in these types of computations.
And
People
that is not enough for you to
well,
give you the index.
it's a bit. In principle, yes, but
something like this was done for just an ordinary zero-two theory.
that's right. So whatever you can do, exactly. So there you have a maximally supersymmetric Yang-Mills theory. You can compute the S5 partition function. The point is that these things are hard to compute. Like the S5 partition functions are hard to compute. Yes, and I would say, well, one reason I am skeptical in claiming the victory is because this technology is very computing this partition function. There are a lot of tricks that you do that are not always, derived. And many times you can say, okay, I want to see an E8 symmetry. I do a computation with some machinery that I think will work. It doesn't give me E8 symmetry, but if I deform the contour and so, I mean, it's legitimate because the technology is complicated. But you see, it's not. I would not call it a check. It's still the technology is not developed enough.
Is there a clear conjecture for these things? It's not. It's
Well,
not an interesting question.
No, it's an interesting question. So I would say a way to compute it would be to make this computation. Do a 5ds5 partition function. Do it correctly, and then you might reproduce the index of the symmetry.
I'm under the impression that the Instagram number becomes one of the patterns of the.
So it's sophisticated. So actually, yes. So there is this U1 in which you turn on holonomy, and there is this instantonic U1, and they actually mix. Like as I mentioned last time, this SO16 is not the subgroup of E8 you see. There it's some accidental enhancement. So actually the enhancement, like to see the enhancement to E8, you need to look on some linear combinations of these two U1s. So it's not that it is just the KK, it also mixes with this U1. So it's not a simple game to play. Okay.
So why is the symmetry? Why should the symmetry not enhance to something that would contain SO16 times U1 also as a subgroup?
Say, what do you mean?
I mean, sorry. So the second line is the 5-dimensional description of the.
That's right.
So.
5-dimensional description with a holonomy.
Okay.
So you turn on a holonomy, you
Without
broken the
holonomy,
symmetry. That's right. You don't expect to have an E8 anymore.
Okay.
You expect to have an SO14 and the U1. It so happens that some combination of this U1 and the KK U1 enhances the SO14 to SO16. And then there is another combination which gives you another U1. But you can play this game. You can compute the partition function, try to see the E8 structure. People play that game. Not too much, but it can be done. Okay, so now let us do some group theory, and what we want to do is to take this theory in 6 dimensions, put it on a torus in our case, and turn on some flux. Okay, so let us discuss what type of fluxes we can turn on, what type of groups, symmetry groups, can we get in 4 dimensions. So the symmetry in 6 dimensions is E8. And we will turn on fluxes for U1 subgroups embedded inside this E8. Okay, and there are plenty of choices. Okay, in principle, we can turn on fluxes like an octet of fluxes for 8 U1s, but we will discuss in this talk only one U1. Okay, we will choose a U1 inside this E8 and turn a flux for it. But even for a single U1, there are a lot of choices. So let me write them down because we will use this later. So there is this group theoretical way of thinking about the fluxes as writing down the Dynkin diagram and then removing one node. Okay. So for example, we can embed, one way to embed a U1 is associated to this node in the Dynkin diagram, and it will, the symmetry that we will get will be E7 times U1. You just look on the remaining linking diagram. And then there are many other choices. So let me write it down, and I will keep this during the rest of the talk. So this, for example, will correspond to E6 times SU2 times U1 symmetry, SU2 times U1. Then we'll have something like this, removing this node, sorry, which will be SO14 times U1, and so on. Let me see if I want anything more.
SO14 times U1, can I think of that as, think of the SO16?
Exactly, exactly. You can think of like SO16 does it has maximal rank.
Yes.
So you can take an SO16 and turn on flux in one of the in one of the SO2s,
Yeah.
and that will give you this these subgroups. And the other are a little bit more sophisticated, but
So that's the holonomy you're turning on.
exactly, you are doing this thing.
Yeah.
Okay. And then there are other choices. I don't know. Let me just write one of them, one additional one, to see that you can get rather complicated groups. For example, this would correspond to SU3 times SU2 times SU5 times U1. Okay? This will be a commutant subgroup that you will get in 4 dimensions. So if you turn on such fluxes, you would expect such groups. So there are 8 choices. Even if you choose only single U1 inside the E8, you get many different theories, many different possible symmetries of 4-dimensional theories that you would get. And they are really different. These are very different groups. And again, I just written 4 out of 8 possibilities. There are more possibilities.
All of them will play a role in what you're going to do.
I will discuss, I mean, we can play, as we will see, and eventually we will define some Lego piece from which we'll be able to construct any of them. And I will discuss this, and this in detail in what follows, but we can discuss any other examples. They will be just complicated quiver theories in 4 dimensions, which are hard to draw on the blackboard. But this turned out to be very simple to draw, and I will discuss them.
And just from the geometry, one will be able to predict.
Exactly, exactly. Like we will see how it comes about, but we will have a single Lego block, which will correspond basically to this thing, and by gluing it in different ways, we will be able to construct anything from group theory.
Sorry, now I'm not very familiar with the E8. I just want to think of it in terms of SO16.
Yes.
So that first flux there, would that correspond, for instance, to all of them equal?
Exactly. Wait for 2 minutes. I will do it exactly in SO16 language.
Okay,
So,
yeah.
but yes, you are right. Okay. So now let me make a couple of comments. Okay, you have these things. You have this U1. So what we will want to do now? We want to predict anomalies of the theory in 4 dimensions, say on a torus without punctures. So a way to do it is just to integrate over the torus this anomaly, 8-form anomaly polynomial. Okay? So we have, this is a way to produce the 6-form anomaly polynomial in 4D. So we need to do, we need just to take this, plug in the values for the flux that we want here, and plug it here. This is a torus, so it's flat. We don't need to twist. It's not very sophisticated. If we have higher genus Riemann surface, we would need to twist to preserve some supersymmetry. Okay? So let me just give you a couple of technical details, which will be.
The grid subflux also needs to be specified.
Sorry?
Which one and also the number of.
Yes. So let me write it now. So for example, all you need to do is just to take this, for example, C2 of E8, which appears in the second Chern class of the E8, which appears here, and see how it decomposes under the groups that you have here. And the way it decomposes is as minus 2 psi C1 squared of the U1 you have chosen. Let me call it U1A. So there is some U1 that you have chosen inside E8. So the second Chern class of E8 decomposes in such a way, plus sum over J C2 of Gj, where these Gj are different factors that appear in the decomposition. And this number is important. This is a group theoretic number which appears here, which is different for different choices of the group. It just, you do the group theory, you see how this decomposes, and you will get some number here. And let me just write what this number is. So for E7, this psi will be equal to 1. For E6, disk size is equal to 3. For SO14, disk size is equal to, I don't remember by heart, to 2. And for this monstrosity, it is going to be equal to, where did I write it? To 15. Okay, a computation. And then for other choices, you will get other numbers. Okay. Now what you can do, you just define some canonical 2 form. Let's call it T, such that integral over sigma of T is equal to 1. Okay, just choose some basis, some form. And then turning on a flux corresponds to writing a very particular expression for this guy, for the first Chern class of the U1 you chosen. That's the flux. So you write it as C1 of this U1A that you have chosen is equal to minus F times T in our normalization. So T is this canonical 2 form. F is the value of flux, is some integer. Or in some cases, it can be a half integer. But it's some properly normalized number, okay? And then that's the flux. But then we can do several things. For example, we still keep this symmetry, this U1, as a symmetry of the 4-dimensional theory. So we turn on also some general bundle for it when we think of it as a flavor symmetry. Okay, just we keep out some, like if the anomaly polynomial will involve this U1, so we need to count the anomalies of this U1, so we still keep something like that. And then we will also, in general, be able to admix this U1 symmetry with the R symmetry that we get. So there is a 6-dimensional R symmetry, but the superconformal R symmetry that we will get in 4 dimensions will, in general, mix with any abelian symmetry which we have. Here, in such decomposition, we will have only one U1 symmetry, the U1 symmetry that we turn on a flux for. So we will just keep track of that. This we don't have to do, but we'll turn on some parameter epsilon, which is the mixing of the two U1s, of the U1R symmetry and the global symmetry, for which couples, well, which multiplies the first Chern class for the R symmetry. And then when we are done computing our 4-dimensional 6-form anomaly polynomial, we should extremize with respect to epsilon to obtain the superconformal R symmetry. This is the procedure of A maximization.
In order to compute the 6th form, you just use the integrate equals.
You just integrate and you use this fact. This is, you just expand. You make this substitution, these two substitution in whatever the anomaly polynomial you get, just expand it, and basically you look for things which are linear in T and keep them. These are the things which are of interest to you. So it's rather straightforward computation, although there are, as you can imagine, there are a lot of technical details that you need to be very careful with. But I mean, you can write a Mathematica notebook which just spits out an answer, and as a matter of fact, this is a project I gave to one of my beginning students just to write a machine that feeds, you feed to it the anomaly polynomial, and then, the machine does the group theory, which fluxes you can turn on, and it spits out the anomalies in 4D. So it's a rather straightforward procedure, and that's how you do it, okay? The bottom line is that you can compute anomalies. So you can compute the anomaly polynomial in general, so it involves a lot of information. In particular, you can compute A and C, okay? So let me write A and C here, because I want to keep it. So with the choice of only flux in one of the U1s, you do this computation, you get the anomaly polynomial, say which is a function of this epsilon with the mixing parameter, you extremize, okay? And you get that the superconformal anomalies A and C satisfy the following. So A is equal twice square root of psi f, where f is an integer, which counts a flux, or again, it can be half integer in our normalization, and C is 5/2 square root of psi times the value of flux. Okay, this is a prediction. So if you find a 4D theory which corresponds to torus compactification with this value of flux, these are the anomalies that this theory should have. And the generalization.
Sir, this is coming. Wait, sorry.
So you compute AI6, okay?
No, but, when you read off A and C, you are presumably just looking at R.
Okay, so the way you do it, the way you do the computation, exactly. You look at the anomalies, which in the linear anomaly and the cubic anomaly, and then you write the trial anomaly. Say A equals trace
Yeah, so
9 trace R to the cube minus 3 trace R, and this will be a function of this epsilon, and you extremize, and that's what you get. Okay. So this is the result of computation, and I hope it's more or less clear how you do this computation. Okay. The generalization of this to many number of fluxes is rather straightforward. Okay, so instead of square root of psi times f, you should just under the square root, you sum over psi i's fi squared in some convenient basis. And here, Shiraz, your comment becomes relevant. What is this basis? There are many bases you can choose. So this basis in which it is correct satisfies certain orthogonality properties that I mean, different fluxes should be orthogonal. And one of the most convenient bases is the SO16 base. Okay, and so I will write it down because we will use it later.
Sorry, can I embarrass myself? C2 is trace FYJ? Is that right?
Yes, it's a thing with 4 indices that you integrate.
And you have C2 of EA is 2C. There's a square of the U1A is
so
C1 is trace F.
C1 is trace. So the C1 has 2 indices. So C1 square will have 4 indices and so on.
But I think that U1A was
the thing in which we turn on the flux.
the thing in which we turn on the flux. But its indices needn't have been on the torus.
No, it needn't be.
Just yeah.
So this is one thing that you need to be careful about when you compute this thing. So how to contract the indices. So there is some, but it's not. That's eventually when you compute it. But when you write this thing, you need to write everything.
And also this C2 is a trace.
That's right, yes.
So C1 squared for U1 and C2 for U1 is the same thing. There is no such, you don't call this C2 because there is no trace to be taken. So that's what I mean.
Say it again?
C2
Yes.
and C1 squared.
They're not the same thing in general.
For U1.
For U1, they are the same thing, yes.
And the fact that every term is proportional to F is just the fact that you started with something with 8 indices, you're getting something with 6 indices, so 2 of the indices have to be.
Well, this is actually not so easy to see. It's basically a property of a torus after you do the computation. In margin, like for other surfaces, this will not be true. You mean the A and C anomaly is proportional to F?
The whole anomaly polynomial.
No, it will not be proportional to F.
I had thought that what's going to happen is that all the remaining indices will be 6-dimensional.
Yes.
The only indices that were in the torus
But
dimension.
there are also gravitational anomalies and so on, which don't know about this F at all. So you can write other.
Right, but on the torus.
On the torus
is 0.
Exactly. So on the torus, that yes.
The whole anomaly polynomial will be.
Exactly.
Right?
Yes.
Yeah.
All anomalies. Well, that's again not completely true because there are symmetries which are not like there are these parts of the symmetry which don't know about F at all, right? Okay, and you can get some mixed terms like something which will be proportional to T times that, and this will, like for example, one way to think about it is that you will have some anomalies for other components of the symmetries which will be independent of F. That doesn't matter which flux you turn on, there will be some anomaly.
That is turned on this torus is only proportional to F.
Yeah.
So that's why you said that's linear terms in T that you pick up, which would pick up things only proportional to F.
That's right, but
unless there is some background curvature, which would be.
Oh yes, I think you are right. Yes, I think what I said should be true for higher genus, but on genus 1 you're right. Yes, this is the only source of curvature. You're right. Okay, so let me now get to the basis. So what type of basis we will use, and it is important for us because that's how we will organize our four-dimensional theories. We need to choose a basis of fluxes, and the convenient basis of fluxes is SO16 basis. One reason why it is convenient, because it's very intuitive. It's just, sorry?
It's familiar.
It's familiar for many reasons, okay? Just an orthogonal group. So we have just an octet of fluxes which form this SO16, and again, you just decompose SO16 into 8 SO2s, and that's those the fluxes, those the ones we're talking about. So for example, a unit of flux in SO14 in this thing will be a vector in proper normalization. There will be a 4 here, but it doesn't matter, and all zeros. Very intuitively, just take one SO2, and you have the rest of SO14s. Now, this is not the only choice of flux. So there are, you can act with on this with the Weyl symmetry of E8. So there is the Weyl symmetry of SO16, which acts in a natural way. You just permute. Okay, but there is also the Weyl symmetry of E8, which is a bigger group. So it's not just these intuitive things, but there are other things. For example, 2, 2, 2, 2, and all zeros is also flux of this sort. And this is harder to see because you need to act with the E8. Another thing which I want to mention, and that Shiraz already said, that the unit flux in E7 is just everything once. Okay? This you don't guess, you need to compute. How Shiraz guessed it? You need to ask Shiraz. But okay, but
it's like a spin. It's like proportional to a spinner.
Yeah.
And so it would preserve some sort of, I don't know, I just felt.
like it's a bigger symmetry, and this is the most symmetric thing. That's not, I mean, I don't have a very
what is the
fast
actual
argument. So E7 has an SO12 subgroups. I don't know if. Okay, and then let me also mention this thing. So this is the SO14. The E7 also has another representation, which is 1, 1, 0, and then everything zeros. This is another E7. We will use it also. So again, this you use the Weyl symmetry of E8, which is not, which is an extra to SO16, and the E6 times SU2 is 1, 1, 1, like 6 ones, 1, 2, 3, 4, 5, 6, and 2 zeros. Okay, and this kind of, this is an SU6, and like an SU6 and SU2. That's maybe U6 and U2. That's how you can understand why it is an E6. And we will use later on these values when we'll proceed. Okay, so this is what you need to remember from group theory. Okay. So the next step is to understand what happens in 5D, and I discussed it during the seminar. So to understand what happens in 5D, we need to understand what we will eventually want to do is to understand what are the theories corresponding to tubes with two punctures, with two holes, spheres with two holes and some value of flux. So to do that, we need to understand punctures, and to understand punctures, we need to go first to 5 dimensions, as we mentioned before. So the way to understand punctures is to first to compactify to 5D on a cylinder, on a small circle with a cylinder. Then you get this effective field theory in 5 dimensions, and then you cut it. Okay, you introduce a boundary, and then you should discuss boundary conditions. Okay? And one particularly interesting boundary condition which preserves the right amount of supersymmetry is giving all the gauge field the Dirichlet boundary condition. And then we have 8 hypermultiplets, and we can think about these hypermultiplets in 4-dimensional n = 1 language. And then we give 8, like 8 chirals, whatever that means in 5 dimensions. We give the Dirichlet boundary conditions. And the other 8 chirals, we give Neumann boundary conditions. So this is, and the claim is that these boundary conditions preserve half of the supersymmetry, and half of the supersymmetry here is 4 supercharges. Okay? So these are the boundary conditions that we give. And then this defines for us a puncture because we have given a Dirichlet boundary condition to the gauge field. We freeze the gauge field at the boundary. And it oscillates in the bulk, but on the boundary we have fixed it, and large gauge transformations correspond to flavor symmetry. So we introduce for each puncture an SU2 symmetry in this case. So each puncture comes with an SU2 symmetry, which is the gauge symmetry of the 5-dimensional description. Okay? Now, it's not just that. We introduced SU2 symmetry for the punctures, but remember that this theory in 5 dimensions had this SO16 symmetry, rotating the scalars in the hypermultiplets. But because we have given non-democratic boundary condition, not to all 16 we gave the same boundary condition, a puncture, actually this type of puncture, breaks SO16 to SU8 times U1. Okay?
Wait, this SO16 was in the absence of holonomies on the circle?
No. It was, we always have this holonomy on the circle.
This was the SO14 that got enhanced to its SO16.
Yes, exactly. Okay, so
But
what?
This, sorry,
Yes.
but this was a particular kind of holonomy on the circle, right?
Yes, this is the holonomy which gives us a gauge description in 5 dimensions.
But you will be turning on other kinds of holonomies as well. I mean,
No. We will only discuss, okay. We will define the punctures using 5D description, which has these types of holonomies. These are fluxes. This is a different thing. So this is, in the end of the day, you should think about this as an intermediate construction if you don't want punctures. It is important to define the punctures, it is important how you went to 5D. And we will only discuss punctures which come from this construction. But when you close to a closed Riemann surface, this should not matter how you define things, because it's just an intermediate step. Oh, the only thing which will matter is what is the flux that you have turned on.
The connection is still flat here.
Yes, the connection is flat. Okay?
yeah, I'm sorry, but I was thinking of this, suppose you think of the flux as a varying holonomy.
Yes, we will get there. We'll get there in 2 minutes. Okay, so but now I want to emphasize that the puncture introduces symmetries, like every puncture comes with a factor of SU2 symmetry, but also it breaks the 6D symmetry, which was E8 in the beginning, to a subgroup, which is SU8 times U1. So for example, if you have some flux, which already broken the symmetry, say to E7, then you further break it to SU8. And if you can, in principle, have 2 punctures which break to SU8, but this SU8 is differently oriented inside E8. So there are many choices in principle. And so the symmetry that you will preserve in 4 dimensions. Sorry? No, well, yeah, I don't know of a shorthand how to compute it, but you should just compute it. You know, whatever. There is some symmetry that the flux preserves, and there is some symmetry that punctures preserve, and the symmetry that you will get in 4D in presence of punctures and flux will be, you know, the commutant of the, well, yes, in a sense. Right. Well, yes. Okay.
And here, why do you discuss only this possibility?
Okay, there are other possibilities.
Same table, right?
Well, this is this is the possibility which preserves the maximal symmetry.
But other holonomies.
Which holonomies? Here there are no holonomies, just boundary conditions.
No, but you have a holonomy, right? Which is what gave you.
Oh, yes. Well, the question you need to ask, if you turn on some holonomy, what is the 5D description? And then you need to analyze this question.
Yeah, so here, you mean what I'm getting is that you will consider various fluxes, but for holonomy you will only consider one particular embedding.
Exactly. Yes.
So the other embeddings of U1s.
It's just. You mean U1s which preserve other subgroups. Yeah. They are interesting, but I don't know what the gauge theory description is away.
This is the only case where you know this 5D.
That's right. This is a case where I know the 5D description. You might not turn on a holonomy at all, but then we know that you will get a 5D Seiberg E8 theory, okay, which is strongly coupled to SCFT. Okay. Okay, so this is the story of the puncture, and now again just a couple of comments. Okay, how do we compute anomalies of the punctures? Okay, now we have these SU2s, and the Riemann surface is different. The computation that I have outlined before was for a torus, okay, with no punctures. Now we have a sphere with 2 punctures, which is also a flat space. So the computation is not very different from what we had before, and let me just say here that there are 2 types of contributions to the anomaly in presence of punctures. And let me be more general, not just torus, but general genus G Riemann surface.
I'm sorry, I'm just going back to
Yes.
Peter's question. In the most general theory, the punctures will, I know you're going to close it for the torus, so
Yes.
there won't be punctures in the end.
Yes,
But in general, you have punctures remaining.
that's right.
And then it looks like there are many inequivalent kinds of punctures.
Exactly. It's actually, okay, yes. You want to go there? I will go there. Yes.
I'm sorry.
No. Punctures introduce an enormous amount of complications in general. In general, the choices that you mentioned, we typically call them colors of punctures. Okay, and the colors of punctures, there are a lot of different things you can do, and they correspond to these different embeddings. And different punctures will give you different theories. It will just like you can have, for example, a 3-punctured sphere with, say, all colors the same, say with the same value of flux, or say 1 embedding and 2 others with different embeddings, and these can be completely different theories. And one needs to analyze what happens. Moreover, even for a tube, you can have different colors here and there, and there is a large zoo of possibilities, and I just don't want to go there in detail because it's
Too big.
it's another layer of complication, which is not, I mean, it is there. If you want a complete picture, you need to understand. And for these types of punctures, which are maximal, which preserve SU8 times U1, we have the picture, we understand, but there might be other punctures which we even didn't classify at the moment.
But in the maximal supersymmetric case, this is classified by the norm equation, right?
That's right. So you would need to do the analog of that computation. Like, what are the supersymmetric boundary? It's basically the analysis of supersymmetric boundary conditions here.
And choices of holonomies, right?
Well, the
Also
choice of
holonomies.
holonomies, again, we only know about this procedure is useful if we know a gauge theory description in 5D, and we only know the gauge theory description for the anomaly, which gives us a 14 times U1. There might be other types of punctures, but we don't have a quantitative control over them.
Right, but in just classifying them,
Yes.
different holonomies will give you distinct punctures, right?
Yes, presumably yes. Again, there might be some equivalences. You do some holonomy, you do some boundary conditions. I don't know. This hasn't been classified, so I don't know. Even in class S, this wasn't completely classified. Okay. So now I just want to make a couple of comments how you compute anomalies in presence of punctures. So there are 2 contributions to anomaly in presence of punctures. One I call geometric, okay? And that is just you do the same as we did before, but instead of genus G surface, you have genus G with S punctures. And basically, you can, if you already perform the computation for genus G, and say you have genus as a parameter, the only thing you need to do is take G to G plus S over 2 everywhere in your generic equation. Or you say on the torus, you need to work, if you just compute it for the torus, you just need to integrate over surface with punctures. Over the cylinder. So it's very straightforward contribution. And for example, sorry? It just
Number of holes.
Yeah, it creates those holes. But why
Okay.
is it equivalent to having?
so the thing, like the Euler character will enter the game, and the Euler character, you know, up to normalization of factor of 2 is this. So if you only it will enter the computation, and if you compute it without the punctures, you will have such a dependence, and then just shift the genus by S over 2. So
It's the same as the counting of dilettante street.
exactly. So this is a very simple thing to compute. Another thing to compute is to compute the anomaly inflow from these 5 degrees of freedom that you have there. And there, the kind of a rule of thumb is look on the chiral fermions that you have in 5D, which have Neumann boundary conditions, and compute their anomalies as if they were a four-dimensional field, and take half of that. Okay, and why half? Think of just a hypermultiplet, okay, just free hypermultiplet on a cylinder. Then when you
I spaced out. Take half of what?
so compute whatever. So look on the chiral fermions that you have in 5 dimensions, which satisfy Neumann boundary conditions. Then think of them as 4-dimensional chiral fermions. Compute their contribution to the 4D anomaly, whatever they would contribute, but take half of that contribution. And the reason is, think of compactifying on a finite cylinder, just free hypermultiplet, okay? Then it literally becomes a free chiral field in 4 dimensions. And it contributes some anomaly, something to anomaly, but you should think of it contributing here and here. So if you want a contribution only from one end, you should take half of it. So
like the lattice doubling.
Exactly. So it's very, very simple computation. Just count the fermions and compute their contribution, and then you will get the anomaly in presence of
Sir,
punctures.
this is somewhat of a sideways question.
Yes.
But this prescription works for fancier functions also? Colorful?
It's anytime you have a Lagrangian description in 5D, it will work. You just count the fermions. Okay.
And the puncture will have a flux on the tube as well, right?
Oh, yeah. So puncture, think of it as local. Locally, there is no flux. There is nothing. Like we will push the flux away. I will now discuss the flux, but think of it as the only thing there is just
Without the flux.
without the flux.
Right.
Okay, and then flux is localized somewhere else.
Am I thinking of this going to infinity or?
No. So this part is going to infinity, but this is truncated. This is finite here. And then you think of it as far away from everything else. You don't think, like in this logic, we're thinking of it shrinking. Eventually, that's what we will do. We will compactify on a finite size cylinder, and we'll go to distances which are much higher than this distance, to IR. Okay, so this is one ingredient that I want to mention, and then I remind you about the flux. Okay. So I will wipe this away. So the flux we discussed towards the end of last lecture, and we claim that we can think of the flux, if we have this cylinder, we can think of the flux as a domain wall, interpolating two different values for holonomies. And schematically I write it as m and minus m, but it can be different embedding of this U1 into SO14 and so on. Okay? So, and again, the reasoning was that you can turn on a space like a holonomy, which depends on this direction, and this produces a flux with like positive definite f, that when you integrate over this thing, you will get some value of flux. Okay. So, and then by choosing your parameters properly, you can localize the flux somewhere here, but it will interpolate between two regions where the gauge theory description will be different. There will be different values of parameters. And then properly choosing these parameters, you can produce different types of domain walls corresponding to different values of fluxes. And this is kind of an art to do.
So this m and minus m, in the simplest case, these two will be wide related?
Yes, so the simplest thing that you can do in theory, as we will see, this is not the simplest domain wall that we can build, is just this SO14 times U1 with just different opposite holonomies. Okay?
So that you can compactify them.
And then you will get actually as an SO14 flux.
Yes.
Okay.
So the flux this way of the thing is quantized.
Yes, and on top of that, you always need to be careful to properly quantize whatever you put here. Okay, so now I will just tell you so now when you do this thing, the way to understand it is that there is some 4D theory living on these domain walls, and it is coupled to the bulk degrees of freedom. So now the game is to understand what is this 4-dimensional theory. And there is no clear-cut algorithm how to do so. So one way to do so is, for example, guess the answer, okay? And then compute compactification down to 4 dimensions and see whether the theory you get in 4 dimensions has the right anomalies, Okay, you compute the anomalies from 6 dimensions using these punctures, also the contribution of the punctures, and see whether the anomalies of the theory you get is what you expect. And what is the theory in 4 dimensions? The theory of 4 dimensions is just this 4D the 4D theory living on this domain wall, plus the fields satisfying Neumann boundary conditions that you have in the bulk. That's it. Okay. So now I will just drop on you an answer for such a computation, but which was obtained in this with this kind of logic and doing a lot of consistency checks.
That's ambiguous also, right?
Why is it ambiguous?
Because then you could just add a...
It's not a proof. It's not a proof. You're right. Like
You could add a 4D theory with the 0 anomalies.
that's right. But okay, 4D theory with 0 anomalies is a very sick theory. Okay, you can do that. The only question, okay, the only question you should ask yourself, if as we discussed in the previous lecture, you can have different UV theories flowing to the same theory. So you can come up with some theory, and then you can add to it anything such that you will not change the IR behavior, and that will be okay.
Yeah. That's
Okay.
Yeah.
And we will get to it soon, to such an effect.
Wait, maybe I was just checking. You're doing a naive anomaly calculation with the replacement of genus with number of holes, and then just add to that the anomaly polynomial of this 4D theory.
So soon we will. I will now postulate what the guess for this domain wall theory is and what the 4D theory is, and we will perform numerous checks, and you will see how it
But
goes.
suppose you've given me the guess, then I want, let's say, the anomaly polynomial of the full theory in 4D.
Yes.
Is it this calculation you described with genus goes to genus plus holes?
Very good point. So the computation of the anomalies I described doesn't at all talk about this domain wall. This domain wall we will use to derive the 4D theory. But the computation of anomaly is not, you just integrate the anomaly, the 6D anomaly polynomial on the Riemann surface, and add the contribution of the punctures. That gives the full answer.
Oh.
Okay? So this is a different, this piece is to derive the 4-dimensional theory.
Effect of the fluxes.
Exactly. Yes, exactly. The fluxes we take into account from 6 dimensions. The only contribution to anomalies from 5 dimensions is what happens at the punctures. That's a very good point, because otherwise there wouldn't be any non-trivial consistency check. Okay. So a claim, if you take flux, which is half, everything half, so it's a half unit of E7 flux, then the theory on the domain wall is just the following thing. Okay? So think of it like that. There is an SU2 here. There is a different SU2 gauge here. And there is a on the domain wall, there lives a bifundamental field, which is charged under this SU2 and charged under this SU2.
So I missed what this SU2 was.
So now I'm telling you what is the theory living on the domain wall.
2 SU2s.
Oh, in 5 dimensions we have an SU2 with 8 flavors, right? This is the gauge theory we have in 5 dimensions.
Sorry, yes.
And this domain wall interpolates between two different SU2 gauge theories. Okay? So the degree of freedom which is living on this domain wall is the bifundamental of 2 SU2s. Let's call it Q. This field, this bifundamental is called Q. And this X is another chiral field. I don't know how. Let me call it phi. So this X is phi. And there is a superpotential, like determinant of Q times phi. Okay, this phi is singlet of the 2 SU2s. Okay, so there is a determinant like QQ with epsilon that you compute, multiplied by phi, there is a cubic superpotential. That's the claim. What is the theory on the domain wall? And soon we will subject it to test.
Symmetries now should also match, right? Because you have, in order to define that cylinder, you have a turn on holonomy, right?
Yes.
And then you have also turned on a flux which is of E7 type.
Yes.
So now the resulting
Yes.
theory you should have a symmetry which is
That's right.
which is some commutant of this kind.
That's right. So how exactly to do that? In this, in this, there are 2 ways to do that. There is a way to guess an answer and then check it. That's how we did it, or rather how Kim and Gaiotto did it. And there is another way to try and figure out what exactly holonomies you need to turn on, and you know, what are the profiles of the space-time dependent holonomy and so on. This wasn't done. This is a harder question, and the answer is very simple in the end, and it undergoes a lot of checks, as we will see. But it's a good question if you can do that. It wasn't done.
I missed the question. Could you just say it again, please?
No, I was just saying that
It's the symmetry of this domain wall theory you're
No,
talking
no.
about?
of the 4D theory that you would obtain after reducing over this whole thing, right? So there are two things. There is one is the holonomy has been inserted on the leftmost end, let's say, right?
Yes.
And now flux is inserted, so it would interpolate to some
That's
other
right.
holonomy,
Yes.
right? So now you have holonomy and a flux, and
Yes.
those choose two different
Yes.
U1s inside.
Exactly. They are choosing two different ones, but like two different U1. Each one preserve different U1 times SO14, such that the flux will be in E7.
So this is the symmetry preserved when you take this full theory, this full 5D theory, and put it on a double-ended cylinder.
Yeah.
Yes.
This is the 4D theory you get when you
Yeah,
do that.
which would have a lower symmetry. Right?
That's right.
Yes. But have we heard what that 4D theory? This thing was
Well,
just
I'm getting there. So this is just a theory on the domain wall, okay? But then we have this.
Just, yeah. Yes.
Give me a minute, and then we'll discuss. So this is a theory which is stuck on the domain wall, and it is coupled to the bulk theories. Now we want to compactify this cylinder down to 4 dimensions, and we only keep the fields which satisfy Neumann boundary conditions. And what are they? They are an octet of this SU8 that remember that the boundary conditions are Dirichlet for A, and then Dirichlet for 8 chiral fields, and Neumann for 8 chiral fields. So we are keeping these fields. So they are an octet of SU8, and they are charged under SU2. So that's the theory that we get in 4 dimensions. Okay, that's the claim. This is the theory with superpotential, which corresponds to this triangle, plus this superpotential. It has manifestly SU8 times U1 symmetry. So SU8 you see here. There is another U1. There is actually yet another U1 which is accidental. There are 3 types of chiral fields, so there are, and only one superpotential which relates them. So there are in principle 2 U1s, but one of them has no clear higher dimensional meaning. Only one of them has higher dimensional meaning. And this is the theory. We will correspond to a cylinder with this value of flux. And this will be our basic building block with which we will play. Extremely simple theory, a West-Zumino model. That's it.
Sorry.
Okay, so now ask.
Why is the 8 charged on both of these? Is it on the, you're talking about the torus or double integral?
No. So there is an octet of field here. There is an octet of fields here. So this is one copy. This is another copy.
So that's 8 and 8.
8 and 8.
Right?
Exactly.
The symmetry should have been SU8 times SU8.
No. It's the same as the 6D theory has only one E8. We should correlate these E8s. There should be something which correlates this E8.
Is it the boundary condition? Is it
No,
the
no.
reflection?
No. The domain wall should have such interactions which correlate between the two SU8s. Okay, it's like there was this work by which this is actually extension of that work to 5 dimensions of Gaiotto and Witten.
Sorry. This is superpotential.
Exactly.
Okay.
Yes, this is a superpotential.
I thought it was some gauge interaction.
No. It's a West-Zumino model as simple as you can get. Okay, and the claim is that this West-Zumino model corresponds to this to compactification on a cylinder with this value of flux. One immediate check that you can do is to check anomalies, compactify on this surface. You get some anomalies. They perfectly match the anomalies of this West-Zumino model with these particular interactions. Okay, but yes.
Q and phi, tell me again what they were, please.
So Q is Q and phi. These are so Q is the bifundamental, which you should think of it as living on this domain wall, and also phi is the gauge singlet field, which lives on the domain wall. So the theory, which the matter content of the domain wall is just this bifundamental and this singlet field.
So this is not the superpotential that breaks the SU8 times SU8.
No. This preserves everything.
Everything. But then in addition, there's some other superpotential.
Right, which correlates between these SU8s and SU8. Okay. So now we are basically done with our derivation. And
Sorry, Shlomo.
yes.
The gauge is gone because all the gauge fields have Dirichlet boundary conditions.
Yes, that's right. Okay, so what we will do now, we will use this building block. This is our Lego piece, which corresponds to this value of flux. And now we can construct anything, any torus. We will see how we can construct any torus we want with any value of flux, and we will see how the symmetries will emerge.
Sorry, this is probably not important, or maybe it is, but this you told us about matching anomalies.
Yes.
Now the anomalies are independent of the superpotential.
Well, they know about superpotential in a tricky way. You only are allowed to compute anomalies of symmetries which are preserved by superpotentials. Only in that way they know about the superpotential. And R symmetry, of course, is constrained by the superpotential. But modulo that, like what is the coupling and so on, it's independent.
Sorry.
Yes.
When you say you match anomalies, you predicted anomaly with the STI anomaly theory. Do you also match the ANC?
Yes, everything. All the full anomaly polynomial. You match the full anomaly polynomial.
Then one would imagine that it would be unique.
I don't know. Again, there are cyber dualities that you know about. There are two different UV theories which.
No, at the CFT level.
Well, yes.
There
There is a unique CFT. There is. Well, okay. I don't know of a counterexample where you have two different CFTs which give you exactly the same anomalies.
In other words, the CFT.
That I don't, but I do know of two different CFTs which give you the same ANC. Okay, that I don't know of. And they have the same rank of symmetry, but the spectrum of operators is a little bit different. The same ANC, the spectrum of operators, protected operators, is a little bit different.
Oh,
okay, so now what we are going to do, we will use this building block to make a lot of 4D checks. So now we are completely in 4 dimensions, and we are going to play with this. Yes.
Let me just go back to the statement. Can you say what you said? That you don't know the example of theories with the same anomalies, or you do?
I know examples of two theories which have the same ANC. Actually, you can construct them with these constructions. And they have, the symmetry is slightly different, but in a sophisticated way. Like the symmetry that you see in the Lagrangian is the same, for example. But the spectrum of operators is different. And the IR symmetry is different. Okay? So if you compute ANC, you look here. Okay? Actually, here is an example. So you can compute, perform a compactification which preserves E7, so psi equals 1. Okay? And 1 unit of flux, you get A equals 2, C equals 5/2. Take a compactification which has psi equals 4, which is SU8. I did not write it. It preserves an SU8. And take
all of the things same, AC and global symmetry.
No. That I don't know.
Okay.
But A and C, definitely. Okay. So let us play now. So the rest of the lecture will be just a game. Okay, so let me write this theory again. Okay, so the conjecture is that if you have flux half, everything half, on a torus, on a cylinder, the theory is just this, SU2, 8, like that. Okay? Now we can produce from this other theories by gluing things together. Okay? And what is the gluing? The claim is that the gluing is just take two such blocks, take them near each other, and introduce another octet of fields. This is like the octet you lost, the one which got Dirichlet boundary condition, if you wish, and gauge the diagonal contribution of this. Let's call this I didn't give it a name. Let's call this small q, and this small q prime, and this small phi. So the superpotential you introduce is q phi, say plus q prime phi. Okay? There is this field coupled to this, and this field coupled to this. So in this particular case, this is a field. So these are just mass terms. So what happens when you do this gluing, the theory that you obtain is this theory. Okay, you are left only with one chiral field. So a pair of chiral fields get a mass term, because like a linear combination of two q's gets a mass term and is killed, and a phi gets a mass term is killed, and only one of them survives.
Equation motion of phi will be a set q equals q prime. That kind of.
Yes, exactly. Exactly. Q plus q prime is equal to 0. That's the mass term. So this theory corresponds to sphere. Now let me call this half unit of flux in E7. This theory has a 1 unit of flux in E7. And so on. You can continue. And again, the just adding them. And the anomalies match, everything matches. So now there are neat checks you can do. So Abhijit asked the question last time, there is a flux of half, and what is the flux of minus half? But these are the same theories. Like, there is no difference between a half and a minus half. The difference is, if you wish, how you relatively, you take two pieces, one you call a half, another you call a minus half, and so how you orient these lines, the complex conjugation, okay? So now let me take this theory, 2, 8, like that, sorry, I gauge, 2, and like this, and add to it a piece with with an opposite orientation. Sorry, yes, like that, 2. And I have here, okay? So now the prescription is to gluing things, you don't introduce an additional field, you just, if this is Q and this is Q prime, you just turn on a superpotential, which is QQ prime, because they have opposite charges, okay? But what you get, so this identifies the 8 here, okay, this type of superpotential. These fields get a mass, and then you get an SU2 here. This is the theory. But what is this theory? This theory is SU2 with 2 flavors, okay? It's SU2 with 4 fundamental chirals, which is called SU2 with 2 flavors. Now, if you remember what Seiberg has taught us, that SU2 with 2 flavors has this quantum deformed moduli space. Nowhere on its moduli space you have 0 vevs. So there is something which obtains a vev everywhere on its moduli space. In particular, when you analyze the dynamics, these vevs will Higgs this symmetry. So the statement is that this theory in the IR is equivalent to this thing, as expected. Okay, this is a check of the procedure. This follows from SU2 plus 2 flavors dynamics analyzed by Seiberg. The piece here was flux 1. This piece was flux minus half, so 1 minus half. We should get back the flux a half piece. So this is a very simple consistency condition, a consistency check of the picture. Okay? Okay, flux 0 is very singular thing. And imagine that's basically exactly what you said. Flux 0 is something you add, and it doesn't change the theory. That's why I started with flux 1. Okay, I could do the same thing with flux a half, but then I would get something which is flux 0, which is a bit a weird theory. You know, so flux 0 is typically something weird. It's okay when you glue it, when you combine it with a bigger theory. Then it's fine. It's basically a thing which has all the anomalies are 0. Everything is 0. So you just don't change the theory. Okay.
Sorry, in your Seiberg kind of picture,
yes.
The middle guy was the gauge symmetry.
This is the gauge symmetry.
And that guy, guy at the bottom
is a flavor.
Parts of the flavor.
Yes, these are the 2 punctures.
Yeah.
So this is the picture where we split the cylinder into a part which has a half and a part which has a minus half flux, which should be equal to a cylinder which has flux half.
Yeah, and the Higgsing, Higgs is the gauge symmetry?
Exactly, yes. Because something which is charged like a gauge invariant operator, which you build from fields which are charged under this SU2, obtains a vev.
Yes. So Higgs is the gauge symmetry as well as part of the flavor symmetry?
That's right. It's this flavor color locking. You identify this flavor with this color, and that's how you get it. This is very well-known dynamics. Everything we will do now is very well-known dynamics. So if you wish, if you would not know the analysis of Seiberg, it should have been correct if our geometric picture is correct. Okay? So this is a very simple check. Let me do now, yes?
When you said that flux 0 would be a theory which you glue and get the same thing again.
Exactly.
So that you meant, you took that to conclude that it has a 0 anomalies.
That's right.
Not quite true, right? Because there is some gluing procedure also.
No. So everything together with it's not that the anomalies of it are 0, but together with the gauging, with the contribution of the gluing.
Okay, it seems probably like okay.
Well, it's SU2 with two flavors. It's a theory with quantum deformed moduli space. You can discuss what is the description on this moduli space.
The theory with the zero flux.
I mean, you can make sense of it. Again, it's just SU2 with two flavors.
Five-dimensional point of view. You had
Yes.
you had a puncture, no wall,
Yes.
right? So you have
Oh, from geometric point of view.
diamond,
So
so
in
you just get a
yes,
8 chirals, right?
right. So
And then you would glue. You
So,
would have gauge symmetry,
okay,
you
so let
might
me say it like that. So typically, this construction, you did not see proofs of what I have said. Okay, you saw some arguments. So typically, these arguments fail in very degenerate situations. In particular, zero flux on a tube, the arguments fail. This is not, you should be able to play such games where you have flux 1 and flux minus half. It should combine to something which makes sense. This should be consistent. But flux 0, we don't know what it's just outside of these types of games. You can formally think of this, combining this as flux 0, but this thing by itself doesn't subscribe to the game that we are playing. Okay? Okay, so now that we have this consistency condition, we can play more sophisticated games. For example, we know what the what a tube for E7 is. So now I can construct tubes for other fluxes and how this goes. And this is really, really simple. Okay? So see the flux for E7, let me take, for example, the flux for SO14. This is the simplest thing to do. But in the weird normalization, weird frame. This is the easier thing to do. So there is a SO14 that we said, which is 4 here and everything is 0, but there is such a thing also, related by Wiles symmetry.
The holonomy is still in the 1, 0, 0, 0, 0.
Yeah. The holonomy we used to define the punctures, we forget about it by now, because it's not interesting. In the end, it defines the types of punctures, if you wish, but it's not relevant for the flux.
But if we look at the open cylinder, it has both a holonomy and a flux.
That's right. So that's important for the type of punctures. But the flux is a flux, whatever it is.
Right, but the question of whether the flux is in the same U1 as the holonomy or not is physical, right?
Yes.
So you're saying that the flux here is not in the same U1 as the
Right. So a way to think about it is that there is this SO14 times U1 here on one side. Then there is the domain one. Then there is an SO14 times U1 here. But these are not the same SO14 in general. So for the E7, these are not the same SO14, not the same U1s, but you engineer things in such a way that the flux here is E7. But on each side, it is an SO14 times U1. So it just defines, and essentially the punctures on the two sides are not the same puncture.
Yeah.
Okay?
And the fact that you can do that is some group theory, right?
The fact that I can do what? Oh, that I can do engineer such a thing with the 7 flux, yes.
So for example, with that SU3, SU2, SU5, you may not.
Yes, and as we will see, we will now derive some of the domain wall theories, or more precisely, the theories that you get in 4 dimensions. So for this flux, we got a West-Zumino model. And as we will see now, for SO14 flux, it will not be a West-Zumino model. It will be some gauge theory. But we will construct it from this West-Zumino model. And the construction is very simple.
Sorry, Shlomo, I just have this following question. So on the left-hand side, you identify U1.
Yes.
Right? And in the wall, there is a U1.
Yes.
And on the right-hand side, there is a U1.
Yes.
And there is some sense in which U1 left plus wall U1 is equal to U1 right.
In some sense, yes.
Now, is this a constraint on all these U1s? Or
Again, what I can tell you is that there should be such an identification. We didn't work it out. I don't know to tell you how exactly it happens.
I guess the question is, if you add U1 left and U1 wall, can you always make a conjugacy map so that you can get any
Yes.
any U1 or something like that?
There's a question firstly about whether they commute with each other. Oh, sorry. What would the possible constraint be?
Just that, there are definitely non-equivalent U1s, right?
That's
Yes.
right.
So, for example, it could be that the U1 left plus the.
You see, it
flux
can be more
which is
it can be more complicated even.
usually
So
which may not give you that.
no, it can be more complicated. There is an SO14 times U1 here, And there is an SO14 times U1 here, but this U1 that you see here is embedded in some complicated way in this SO14 and so on.
No, I'm just saying that there may be walls
Yes.
which will not have the SO14s.
Oh, you mean that the walls are correlated with punctures? Yes, that is true. Not with with one particular type of puncture and one particular type of flux. This is fixed.
Okay.
That's true. That is true. That is definitely true.
Yeah, you're saying you might go over to a U1 in one of these other classes.
Yeah.
Right. So, for example, if you want some other type of punctures, you might need to, like your flux is constrained and so on. So that is definitely true. Okay. So let me do this.
And in the case that you just chose to describe now,
Yes.
it just so happened that your choice was clever that both sides were SO14.
That's right. Yes.
And one thing where it would be obvious is you just chose both the holonomy and the flux to be in the same U1.
Yes. So.
It would obviously go.
Then it would be the same thing.
Same thing all the way.
Right. But then you have a flux.
Then something and minus. So.
Yeah.
But he doesn't worry.
But that is not what you had
Yeah.
previously.
Okay. So
Like in the previous case, it's difficult to see that there would be SO14 on both sides. Because in between there is something very
One.
weird.
Yes. It's actually related to the, okay. It's actually related, what you are saying, to the fact that the flux is half integer, and you didn't complain about that, okay? It's related to that fact, and we can discuss it later, but I don't want to go. Okay, so let me engineer this thing. Yes.
Just take side. The gluing prescription was also just came out of geometry, right?
That's right.
Because the things that you had Dirichlet, you just made them normal.
That's right.
And that gave you the glue.
That's right. Okay. So let me now engineer this flux with the things we know. What do we know? We know that there is a half, 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 everything half. This is our E7 wall. But now what we can do is do the same thing, but with 4 halves and 4 minus halves. Okay? This is also E7. It's just an SO16 wild symmetry transformation. We can flip signs of even numbers, okay? It's the same thing. And this just, you sum the numbers.
It's also part of a chiral spin.
Exactly. So now, now we split this 8 that we had into 4 and 4. So one theory is just this, 2, like that, and then there is something like that. So I did nothing. I just split the 8 into 4 and 4. Okay? This is this thing. Okay? But now the other thing is the same, almost the same. Sorry, a 2. But now, because I flipped the sign, I flip the orientation. Okay? So it will be this way, 4, and this way. And now I will glue it. So now when I glue it, since these are opposite orientation, they just kill each other. These are the same orientation, so I trade them with one field. So that when I glue these things together, with the prescription I told you before, the theory that I obtain is this theory. 2. Sorry. I want to change. Like a 2 here. Like that. And then we have 4. And, well, doesn't really matter. Like that. Okay? So this is the theory corresponding to this flux. Okay? So now it is a gauge theory. Okay? It has 2 SU4s which are not on equal footing. Okay? But that's what it is. That's what the prescription gives us. Okay? So now what we can do is take 2 such theories and glue them together to form a torus. Remember? So what is the expected symmetry of this theory? So the flux preserves SO14 times U1, but the punctures break to SU8 times U1. So there is some commutant. There is some symmetry which is not very interesting what it is. But if we glue it to a torus, okay, then we should see an SO14 times U1. Okay? So I will not draw it here, but you just take 2 such theories and glue them together. And you can compute, and you can look at the symmetries that you have. The symmetries that you will have in the UV are these 2 SU4s and a bunch of U1s. And what you will see, for example, by computing the index, that everything forms SO14 times U1 representations. Okay? So this is an example how you get an enhanced symmetry in a very simple way.
Sorry, I mean, you could have said that even in the earlier
Yes,
example,
I will do it. I will do it soon. Okay? Okay? In the same way, I can produce, for example, E6 times SU2. I will just remember that the flux there was, for example, 1, 1, 1, 1, 2, 3, 4, 5, 6, 2 zeros. And with such tricks, I can engineer the same thing. And what will happen there is there will be a 6 here and a 2 here. This will be a thing which should have an E6 times, an E6 times SU2 times U1 symmetry. And we will discuss it soon in more details. Okay? So you can play with these Lego pieces any game you want. These theories are very simple, and you should see enhancements of symmetry. Now I go to this original example that Abhijit wanted me to discuss. Okay, so now let me take the tube that we had, the Wezumino model, and glue it to itself to obtain a torus which has flux 1. So this is the theory. Okay, so this is one Wezumino model glued to another Wezumino model. This is the torus theory. Okay, so now the claim is that this thing has to have E7 representations, for example, when you compute the index. And when you compute the index, it has those representations, and it is easy to see what is the low-lying spectrum. So for example, you will have a 28 of SU8 coming from the mesons here, plus 28 bar coming from here, which is just the 56 of E7, and so on, and you can continue. Now, typically when you play these games, you get these quiver theories, which are a bit complicated. They are simple. I wouldn't call it complicated. Yes?
You could have glued this with opposite orientation.
Yes, but then you would get flux 0, and then you get something singular again. Flux 0 we don't discuss. Okay?
Because I was going to say that you should get the same theory for all the examples.
No, yeah. Okay, so now what we can do, we have this theory. The symmetry of this theory enhances to E7. And what enhances to E7 is this SU8. So now let us do an operation which preserves this SU8, but maybe breaks some other U1. For example, we can give, yes?
So the reason you had half integer charges was so that when you make a torus, it becomes an integrated charge?
Well, the way it was constructed, as we constructed these theories, and when we saw to which flux it matches to half integer flux, and then we found an explanation for that. When you have punctures, you can have something which is called center flux. Like what you need to do, the flux needs to be properly quantized. What that means is that any state needs to have nice properties in presence of such a flux. For example, you accumulate an integer phase and so on. So, and you can allow half-integer fluxes in certain situations if there are some other, there are two types of fluxes that you can turn on that such that everything, like the combined effect is okay, but each part, is improperly.
Lattice condition.
Yes, exactly. So the half-integer flux with punctures is okay. Without the punctures, what you will get is that you will need to break at least part of the symmetry. You will have something like almost commuting, like these are fluxes in discrete, like in Z2 in some discrete groups, and you can engineer them as like almost commuting holonomies, like around two different cycles, which break some of the symmetry. So it's an extra complication to the story that I'm omitting now. But it's a very interesting part of the story. So now what I want to do is to simplify this theory, but preserving E7. Okay? Just look what is the simplest theory I can build, which has an E7. And what I will do, remember that these x's are just gauge singlet chiral fields. So I give them a vev. Okay? I just do a deformation of a theory which gives them a vev. Remember that they couple, I call them phi, I think, and this field I call q, they couple as phi q squared. Okay? So giving them a vev will give a mass term for these bifundamentals. So what you will get in the IR is a theory which is just two copies of SU2 with 4 flavors with quartic superpotential. Like you couple this 28 with this 28 bar. Okay? Now, this theory was considered in the literature by Di Mofte and Gaiotto. They just took 2 copies, literally this thing, 2 copies of SU2 with 4 flavors, and combined them by turning on a superpotential, which couples the mesons of one to mesons of another. Okay? And this theory they called an E7 surprise. So there is a very beautiful paper that they wrote just about this case and argued that this theory has an E7 symmetry. Okay? This is 2012 or 13. Okay? But now we understand why it has an E7. It's just the deformation of our torus theory, which we claim that our torus theory has to have this E7 representation. This is a deformation which doesn't break that property. So this theory has to have an E7 symmetry. Because it's clear because the thing you gave a VEF to is not charged under this SU8, and this SU8 is the thing which enhances to E7. This deformation, think of, you write an index. In an index language, it's very simple. You write an index, and then turning on a VEF is just setting some fugacities to 1 or something like that. But you don't touch the E7 pieces. Okay, so this thing has to have E7. It's a known kind of sporadic fact in the literature, okay, that this theory has an E7. Why the hell it has E7? You don't know, but here is an explanation why it has an E7. Okay. Okay. How much time do I have? Oh.
So the explanation was that you start with a theory that you know has E7, and you gave a web that didn't break that E7.
That's right.
And the fact that the original theory had an E7,
it follows from the right. So there is one caveat that actually the theory I wrote, I try to be careful to say that it has E7 representation. One can argue that actually it doesn't have an E7, and it is a subtlety that I will discuss next time. But in general, like if you as I mentioned before, if you have small genus and small value of flux, there are some weird things that can happen. So for example, this theory has everything in E7 representations, but actually you can argue that this theory doesn't have any E7 symmetry, and I will discuss it next time. But this deformation that you do somehow kills that subtlety, and you not just have any E7 representations, but you have really a 7 symmetry. Okay. So the last thing I want to discuss, if I have 15 minutes, is a very simple example of, even simpler example of enhancement that you can deduce from this thing. Okay. So we have discussed that that the theory that you get, which corresponds to flux in E6, is this theory. Okay, this is the tube, which has a flux in E6. So let me do what I want to do now. It has a half unit flux in E6. What I do now, I just close it on itself. Okay, not 2 copies, close it on itself. And the theory I will obtain is this thing. Just two lines here. Exactly. So you will see what will happen. So something like that. Okay. This is the theory you will obtain when you glue it to yourself. To itself, sorry. Not to yourself, to itself. Okay? So now, when this happens... No. This 2 is by itself. Okay? No, this is flavor. Okay, let me color the flavor. This is 2, this is 6, and these two are gauged. Okay? Now, because you glue it to itself and the flux is not proper, basically you break some of the symmetries which made the flux improper.
I didn't understand what you meant by glue to itself.
Oh, okay. So I just...
Oh, you mean just join the ends?
Yeah, exactly. I gauge a diagonal combination. Exactly. I gauge the diagonal combination of these two, and I add this octet, this bifundamental, sorry, there had to be some fields that I need to add with some superpotential, so I do it in just following the prescription I gave you. This is the theory you get. So the point is that this theory is half unit of flux. Naively, it would be E6 times SU2 times U1 symmetry. That's what you would expect. But actually, you can show that the fact that it is half integer flux is inconsistent with having this SU2. So the symmetry that you expect is only 6 times U1 because of this half integer of flux. Okay? And this is 6. You build from this SU2 and this SU6. And U1, there is an additional U1 here. Okay? And again, you can compute the index and check it. Everything works out. No. No, I'm not going there. Now I'm doing the thing I did before with the A7 theory. I simplify it. It's a simple but ugly theory. But I can now give a VEV to this. Yes.
Before that, you have this half integer flux, and you say that's consistent because you also have some discrete flux.
That's right. But this discrete flux, well.
I mean, now you don't have a puncture anymore.
Exactly. I don't have any puncture anymore. I only have this discrete flux. But this discrete flux, when you had a puncture, you could somehow swallow it into some transformation of the puncture symmetries. Now I don't have these punctures anymore. And the fact that I have some discrete flux breaks the symmetry. The way you should understand it, these discrete fluxes, is that when you have a torus, you can turn on holonomies around 2 cycles, which don't commute in the universal cover of the group, but commute in the group. In particular, in general, when you turn on such fluxes, they break your group to some subgroup. And when you do the detailed analysis in this case, you get that what is broken is the SU2, and E6 times U1 is preserved. Some group theory analysis that you need to do.
You come back to yourself up to a while transform.
Exactly, up to a center, some element of the center of the group, and that breaks the symmetry. Okay, so now I want to simplify this theory further, and I simplify it again by giving VEV to these fields. I claim that E6 is obtained just from this SU6 and this SU2, so this doesn't matter. So what do you get? You get from here a 6, a gauge group here, a 2 here, and a gauged 2 here. Okay, I just erased these things because I gave mass. But now what is this piece? Okay, this is SU2 with 6 chirals. It's SU2 with 3 flavors. And Seiberg has taught us that SU2 with 6 flavors in the IR is equivalent to the 15 gauge invariant bilinears that you can build here. Okay, 6 times 5 over 2, 15. So in the IR, and when we integrate, there was a cubic superpotential. So when we gave a mass to this field, we generated some quartic superpotential, which couples bilinears in this and bilinears in this. So after we analyze the dynamics of this piece, what we get is just SU2 with 4 flavors split like that. And there are gauge singlet fields, the mesons of the dual description of Seiberg, which couple to the mesons here. So there are 15 gauge invariant fields now here. So the statement would be now that this extremely simple theory, just SU2 with 4 flavors, but with superpotential, which splits the 8 into 2 and 6, should have an E6 symmetry. You see, this is an extremely simple statement, which people could have discovered in mid-90s. This theory was widely studied, but it wasn't discovered. And it's a bit weird to split into 6 and 2. It's not natural. From this procedure, it's very natural. And I will also add a flipping field here to simplify things. It doesn't change the fact that it enhances to E6. It just couples to a singlet of the 2 SU2s. And then you can write the index, for example, of this theory. And the index looks like that. Let me write it.
Well, without the superpotential, this would have had a SO.
So without this superpotential, it has SU8. Okay, because there is no superpotential at all. So it's SU8. The U1 is anomalous. So you have only SU8.
But what about the fact that the fundamentals and anti-fundamentals are the same?
If they were not the same, you would get SU4 times SU4 times U1. So the generalization of it is 4 fundamentals and 4 anti-fundamentals. Here they are the same. So this symmetry enhances to SU8. Okay, so if you compute the index of this theory, you get that it is equal 1 plus 27 bar times h minus 1 qp to power 49. So q and p are some fugacities which couple to some combination of scaling dimension and rotation. They are not interesting. This h is, you have a U1 here. So namely, you have an SU6 and SU2, and then there is some additional non-anomalous U1. So this is this U1. This 27 bar is built just from the 15, from this 15, which the flipper fields, the gauge singlet fields, and 6 times 2, okay, from here. So this 27 is equal to 6, 2, plus 15, 1, where the first factor is the SU6 and the second factor is the SU2. And this is the correct embedding in E6 of SU6 times SU2 to produce a 27. Then you have some other terms, and most importantly, at the level, at order QP of expansion of the index, you have minus 78, minus 1. Okay? So at this level, you need to have marginal operators minus conserved currents. You get only negative contributions. This is the current for the U1, and this is the current for the SU8. And it is 35.1 plus 1.3 plus 22. Okay? So there is an additional piece. This is a conserved current for the SU6. This is for U1, and this comes from operator, which looks like, let me call this field QA. And these flipper fields, let me call MA, and this field, let me call QB. So the way this operator 220 is built is some component of QA, QB, and then psi bar of M. Okay, some composite operator built from these quarks, and these gauge invariant operators. Okay, so psi bar is some fermion in this multiplet, in the chiral multiplet of this gauge singlet field. So it contributes with negative sign to the index, and it contributes the extra components of the conserved current. Now, if we identified, under the usual caveats that we identified the R symmetry correctly, this is a proof that this theory has an E6. Okay? Because you literally see the conserved current of E6 in the index. If you did not identify R symmetry correctly, things can move around, and then it might be not true. But under this caveat, this very, very simple theory has an E6 symmetry, okay, in the IR. Although in the UV, you see only SU6 times SU2. Okay? So since I'm, okay, let me stop here. So with this very simple fact, let me stop. The only thing I want to say that you can actually understand this enhancement of symmetry using Seiberg duality. But it will take me time to explain. So, okay, thank you.
So adding these new singlets and the new superpotential enhances the symmetry.
Exactly. It's very funny because you have an SU8. Yeah. When you introduce the singlets, you break the symmetry. You break it to SU6 times SU2 times U1, but it enhances in the IR to a bigger symmetry. To a symmetry such that SU8 is not a subgroup of it. So, but SU6 times SU2 is. So it's extremely simple theory with very nice symmetry enhancement. So, you usually think that E6 is something which is hard to engineer, but here it is. Maybe the simplest interacting CFT that you can think of. You just deform it by a superpotential, and you get an E6. And again, the way we arrived at it is by this contrived logic, by going through 6D, getting theories on tori, but then asking the question, okay, these are some complicated theories, how we can simplify them, and then, but by keeping the enhancement of symmetry, and eventually you can arrive at such theories. If you consider more complicated fluxes, in general, you get huge quivers, and but you can perform these checks of enhancements of symmetry. You always should get the symmetries that 6D dictates, and you always get, and you always should produce the correct anomalies, and you always produce. So this is the simplest example of set of theories with very rich structure of enhancement of symmetry, which you can produce. And again, I try to make a point that you can explain sort of known enhancements and produce very simple new cases of enhancements of symmetry. New dualities from these sets of examples you don't get. I will discuss next time, some new examples of duality that you can get in slightly more sophisticated scenarios.
What about 3-point functions?
Okay, I will discuss it next time also.
You can identify concrete.
For the E string we can, but it's it's more intricate, so I will discuss it next time. But for the torus, everything is completely Lagrangian, everything is funny, fine. Sorry? The trinion turns out to be a more complicated construction of the type of the constructions that we had for the Lagrangian of physics. So I will discuss it next time.
So let me ask a general question. Let's say you've got one of these symmetry enhancements, and you've got a flow that, from a theory that preserves a smaller amount of, I'm looking at the flow from the 4-dimensional theory.
Yes.
So along the flow, a smaller amount of symmetry is preserved.
Yes.
Now, if there was a relevant operator, if I look at the IR theory,
Yes.
and there was a relevant operator that preserved the UV symmetry,
Yes.
then such a flow is very unlikely, because the generic flow would turn on that relevant operator and won't hit, it will just move away. Right, so something that makes this story generic is if every operator that preserves the UV symmetry
Forms multiplets of.
is necessarily irrelevant.
That's not true though.
So here there are relevant operators, like which are they are in good representations of the UV theory, but they combine into a representation of the IR theory.
So then the other way of making it natural is that, if there's some non-renormalization along the flow. Right, I mean but these are of course those kind of operators, right, they're chiral operators. So I would say that every non-chiral operator,
Yes.
because those are the things you cannot control, they're just generated however you want along the flow. And if those were turned on, it would be sort of a miracle for this to happen, right?
Yes.
So somehow
No, but I'm sure you can write.
non-chiral operators that are relevant, how would you know?
Well, just What do you mean by they should be? You want them to be singlets of the?
Yeah, they should be singlets of no, they should preserve singlets of the UV symmetry. Okay, so let's say flavor singlets.
But singlets of but actually good. So that I think I can answer. So if you have a singlet, that should not change anything because it is a singlet. It doesn't affect. The enhancement is of the UV symmetry to something bigger, and the singlet, in principle, wherever it takes you, but it doesn't affect the other symmetry.
No, he's saying that there should not be, if this were to happen, charged relevant operators.
Well, charged relevant operators. No,
They
but
would
charged relevant operators you will not turn during the flow. Because they are charged, they would break the symmetry. You can only turn on
but suppose
singlets.
I have a relevant operator that breaks, is it possible to, is there an operator I could turn on that will break the IR symmetry but not the UV symmetry? Such operators can be turned on.
Yes. But in this case, there are no such operators.
Okay,
Because
so
there are.
theory is tight enough.
Because there are, these are charged, and I think one needs to think whether from them you can build a singlet, but I don't think you can.
So how can this be that you can break the?
Suppose the IR symmetry was SO3, and the UV symmetry was. Suppose the UV symmetry was SO3, and the IR symmetry was SO6 or something like that. Right. So there's some vector of SO6 that is uncharged under SO3.
Yeah.
So that would preserve the UV flow.
Yes.
The UV SO3, but would break this.
Right.
And that you could turn on.
That's right. Then there has to be some attractive mechanism which keeps these representations together in some way.
Yeah.
But
I was wondering whether just relevance. Okay, I need to think that.
But you wouldn't know
Which one? What it
I mean,
was.
if it was a neutral operator in terms of UV, you wouldn't know that it was going to be the part of the thing that will enhance it to IR symmetry.
I agree. I think this is more relevant in the example that you said, when the rank enhances. So you have an SO3 enhances to SO6, and then there might be some gauge singlets that you need, like flavor singlets in the UV that you need for the enhancement to happen in the IR. But if the enhancement is only in the, the group becomes bigger.
SO4 going to SO5.
SO4 going to SO5.
You could have a vector which
Yes.
is SO4, not SO5. So rank is the same.
But which operator you want to generate?
This vector.
But vector you will not generate because you preserve SO4. You only.
No, the vector of SO5, it will be a scalar of SO4.
You say I see, you will distinguish. I see. So you will generate some singlet, which you want to combine with a vector. Yeah.
Which is the necessary part for enhancement.
Yes.
But because that is now relevant and will turn on.
Yes.
They will
Yes.
move away.
So there needs to be a conspiracy in such case.
Yeah, it needs to be that some operators, I think, because you're doing these supersymmetric flows, a lot of your operators are just protected, right?
Yes.
But the non-protected for the non-protected operators, this should not happen. So it must be some dynamical statement about these theories,
Right.
about the anomalous dimensions of certain operators.
Right. Right.
I'm not 100% sure. Just a related statement. There's this cute fact about n equals 4 angles, which you may or may not know. But let me just tell you. N equals 4 angles has SO6 symmetry. Now, it's strong coupling just from supergravity. You can just check that every operator that preserves SO6 is that every operator that preserves SO6 is irrelevant around the n equals 4 fixed point. And therefore, it's very plausible that if you start with something with the same field content, so for instance, the Kunishi operator is an example. It preserves SO6, and at strong coupling, it gets very high anomalous dimension. The things that remain relevant are like in the 20 of SO6, right? So therefore, if you start with any theory, let's say you start with some UV theory, with the field content of n equals 4, and just have it preserve SO6, you should expect symmetry enhancement in the IR to all of n equals 4 superangles theory. Yeah. So, see, imagine the RG flows. There's this basin of attraction. There is a fixed point, namely n equals 4 angles. Let's say we're at strong coupling. Okay, so we've got n equals 4 angles. Now, every operator, n equals 4 angles has relevant directions. So if you say nothing about it, you take some generic flow, it will not land up at n equals 4 angles. Like the phi I, phi j. The scalar will be turned on and will flow. Just a mass magnitude. Okay. However, consider any operator that preserves SO6. Every such operator around the n equals 4 point at strong coupling is irrelevant. Therefore, if you start with a generic Lagrangian that preserves SO6, and then you're lucky. You're lucky meaning this is some order 1 luck. You're on the basis of attraction of this thing. Then it will flow back to the n equals 4 point. And then we'll display the symmetry enhancement. So I'm saying that symmetry enhancement happens generically in RG flows
I see.
as a statement about relevance of operators. So this is an example where you might think some miracle was happening, but you understand it because of the spectrum around the fixed point.
Right.
So I was wondering if there was some lesson along those lines for these guys.
Yeah, I don't know.
So one lesson would have been that there is no singlet operator. There is no singlet relevant operator.
Yeah, perhaps something like that, right? Non-protected. I need to think more. thing about the RG flow is that the fact this is working so beautifully